The first thing we're going to do is build this object you see on my screen. And we're going to replicate it. So you're going to get a lesson in replication. This is one of the applications of transformations. We're going to build this as a cylindrical part. Now, the reason it's cylindrical and not block is because the mesh faces will be in the shape of a cylinder. So I'm going to demonstrate some of this basic property of the cylinder command first, and then we're going to come back and build this part. I go to the Parts menu, click on Cylinder. We're going to have an index list in the I, J, and K direction. But unlike the block command, the cylinder command requires radii for the list that corresponds to the I, angular coordinates for the list that corresponds to the J list. Now the K list and the Z list are just like in the block command. And that's the nature of cylindrical coordinates. So I'll create a very simple cylindrical part. Now there are things that you should not do with a cylinder, and I'll demonstrate that. The cylinder part is not as useful as you may first think it is. So I'll start out with a 1, 11, 21, and then for angular coordinates, 1, 11, 21, and for the Z direction, 1, 11, 21. Now I have to give it radial coordinates, and I'll give it 1, 2, and 3. So we'll have one partition with a radius of 1, a second partition with a radius of 2, and the third partition with a radius of 3. Now for angular coordinates, I'll start at 0 degrees, and then I'll go to 45, and then finally to 90. And in the Z direction, I'll go 1, 3, 5. Let's see what I made here. Well, there it is. It's a block, but it's in cylindrical coordinates. Now you can move things in this part just like you can in the block part. For example, I could select the first face in the I direction, and I can now change its radial coordinate. So I'll move it only in, now we call it the X direction, but really it's in the radial direction. So X takes on the role of radial, Y takes on the role of angular, and the Z is the same as in the block part. So by selecting X and moving in the screen plane, I'm going to move this as a rigid body. In the X direction, you can see that as I move it, it gets smaller and smaller until it gets to the very center, where the radius is 0, and then it turns inside out. Now, if I let go, you'll see that it does this crossover at the center. And this is why cylindrical parts have limited applications. It's fine as long as your part is bounded away from the center. But if you have to go into the center or cross over the center, then you should not use cylindrical part. Now I could also move in the angular direction. If I tell it to move that in the X direction, of course we could take just the maximum I and change its radius. So interesting effects. And that's, in a nutshell, how the cylindrical part works. Now we're going to create a part that is an angle of 30 degrees from here to here. And we're going to put a hole in it, make it round, and then we're going to copy this part 12 times. Now in this cylindrical part, we're going to have in the radial direction partitions at 1, 7, 12, and 14. So here's 1, 7, 12, and 14. And in the angular direction, at nodes 1, 5, 9, and 13. 1, 5 for the hole, 9 for the other side of the hole, and 13. And then in the third direction, in the K direction, just 1 to 10. And what we've got here are the radii corresponding to the 4 indices in the I direction, with radii at 3, 5, 6, and 7. 3, 5, 6, and 7. And the angles will go from 0 to 10 to 20 to 30, and in the Z direction from 0 to 6. So let's build this part to begin with. I'm going to cheat by copying and pasting. So now I'm going to paste that command into the window. So now the next step is to delete a block that we don't need. This is the block where we're going to put a hole. And if we go to our computational mesh, it's this middle block here. So there are various ways that we could select that entire block that goes the total height of the part. I'll show you several ways to do it. One way would be to come up here, move the mouse close to this vertex here and hit F5. And then go down here and hit F6 to get the top face of the block I want to delete. But I want the entire block all the way through. So I come over here to the computational window where the 2 on the K list has been highlighted. Turn that off. When you have nothing selected, as I have here in the K index bar, there's nothing in that bar selected. TrueGrid interprets that as everything in the K direction. So I can either not select anything up here or do a click and drag from one end to the other. I accomplish the same thing. So this is one way to select this block, and you could then click on delete. I'll show you another method. I come over here to the I list and select the interval, click and drag from one end to the other of the middle interval in the I direction, and do the same in the J. And that also selects that block. There's a third way, and that is similar to what we did in the first method. But instead of in the physical mesh, I'm in the computational mesh. I do a click and drag to select the top face. And then come over here and make a correction in the K direction to get the solid all the way through. Click on delete. Now we're going to create a cylinder and project to that cylinder. We're going to want all 4 faces of this region that we just deleted. When you want to do multiple faces, the easiest way is to select the solid. In this case, it's already selected. The solid's gone, but the region that it filled is still selected. And we can now use this to select the 4 inside faces of this hole. Come back to the index bar, click on 2 on the eye and 3 in the eye. That gets us this face and the one that we can't see that's opposite it. And do the same in the J. Click on the 2 and click on the 3. And now we have selected all 4 faces in that hole. What we're going to do is to project those 4 faces onto a cylinder. Now the cylinder, the SD command, surface 1, CY for cylinder, the first 3 are the coordinates of the center of the cylinder. And then the next 3 coordinates is the direction vector of the axis of symmetry. And then this last number is the radius. So I go to the surface menu, SD, surface number 1, cylinder, 5.3, 1.4, and 0 forms a point on the axis of rotation. And then the axis of rotation is 0, 0, 1 with a radius of 0.7. Click execute and quit. So we now have our cylinder. Now there's several ways we can pick that cylinder. One of them is to go to the pick panel and click on surface. So then when we make a little box with the cylinder in the box, that cylinder gets highlighted. That's been selected. Or we could have gone to labels and labeled the surfaces and then go and to the pick panel and pick by label. You come over here and pick the label. There's a third way. Come down here and say surface, type in 1 and hit enter, and that highlights it as well. And then come down here and click on project. So now those faces are constrained onto the cylinder. We can go to display list and say show none to remove the cylinder. It's only looking at the mesh. And now those faces on the inside have been constrained to the cylinder. Suppose that we want the nodes to be equally spaced on this entire face. The RES command, you can apply it to an entire face or to a solid. Now what it does is force this nodal biasing to take place on each edge. Not the edges of the interiors of a face, but the edges on the boundary of faces. So in other words, I'm going to apply this RES command to this entire face. However, internally, all that's going to happen is this edge and this edge are going to both be assigned the same nodal distribution. And the inside will be interpolated based upon the edges. I'm going to select that entire face, hit F1, and it's going to be in the radial direction, which is the I direction. And I want it equal zoning, so I use a ratio of 1. That improved it. The overall mesh is better. If I were to replicate this 12 times, they would not have matching faces at their interface. You'd have one face like this and a second face like this. Now what we could do is apply the res command to this face to get exactly the same appearance as we have here. That would work, but that's too easy. So we're going to use block boundary interface to make this face look just like this face, but rotated 30 degrees around the z-axis. So this will become the master side. So we go to interface, the BB command, hit F1, block boundary interface number 1, and that becomes the master because it's the first time interface number 1 is referenced. All subsequent references to interface number 1 will be on faces that are slaves. So now we select the opposite face. So I turn off J1 and I click on J4 to get this second face. Now we're going to glue this face to this face using the block boundary interface. So we once again use the BB command. We hit F1 to enter our selection. It's block boundary interface number 1. But we really don't want this face to be exactly in the same location. We want it rotated by a minus 30 degrees. The slave has to be rotated a minus 30 degrees around the z-axis in order to match the master side. So I go to apply a transformation, and its rotation around the z-axis, a minus 30. Execute and quit. And now when it rebuilds the mesh, it looks the same here as it does here. We can prove that, if we want to, by changing the master just a little bit. Let's move this vertex from here, this edge from here to here. Let's move it in the z direction. So I go to the move points region in the z direction. And I then, using the mouse, click and drag to move it up to here and let go. And notice this followed suit. So now we're going to learn about replication. And we're going to replicate this 12 times. And as is true with many things in TrueGrid, there are numerous ways to do it. Now what we're going to do is to create 11 coordinate transformations. And then for each one of those, we're going to do a replication of the part and transform it using that transformation. We're going to take this part and make a copy of it and rotate it 30 degrees. Then we're going to make another copy and rotate it 60 degrees, and then 90, 120, and so on. And that's what's happening here. This command, LCT, stands for Local Coordinate Transformations. And there are 11 of them in this problem. And there's 11, not 12, because the 12th one is without any change at all. So we don't have to build a transformation for that one. So the first transformation is formed by using a rotation around the z-axis for 30 degrees. Now we end a list, if you recall. Any list that can be arbitrarily long ends with a semicolon. So this is all that is being used to form the first transformation. The second one is like the first, but twice as much, then 3 times as much, 4 times, and 5, and so on, all the way to a replication with rotation of 330 degrees. This is a table of transformations. It doesn't actually do anything other than define or create the mathematical representation of each one of these in a table. To use them, to actually cause parts to be replicated and transformed, you have to use the LREP for local replication. And we list all of the transformations. Notice that 0 is here. 0 is the identity. That's the one that is the 12th one Doesn't matter where you put it in the list, but it's the 12th one that is no movement at all. So this produces all 12 copies of our part. Now that's a lot of typing. There's an easier way. So the LCT command, 11 transformations, this is the easy way to do it. Rotate around the Z 30 degrees, and then repeat this 11 times. So the first time it repeats, it gets this first transformation. The second repeat is this one, and so on. What it's doing is just taking multiples. Very useful capability, because this is what we do more frequently than anything else, is to repeat in this fashion. This creates all 11 non-trivial transformations. And then we use the local replication and list the transformations. And remember, we can do a sequence with a colon. So when we use 0:11, that means 0, 1, 2, 3, all the way. It's equivalent to this right here. So that's what we want to supply with the LCT command and the LREP. Now, you can use the dialog box if you want, but I find just typing that in is so terse that I don't mind typing it in. Well, I'm going to cheat again, and I'm going to copy and paste. So I use my middle mouse button to paste it in. So my LCT command and my LREP command. So now that I told it what to do, I can now type in merge. And I get my replicated parts. We could have multiple parts, and we wouldn't necessarily use this replication on each of the parts. Or we might. We also will have a global coordinate transformation and a global replication. They both work the same way. But here's the thing. If we were to use global and local, we will get their product. So for example, if the global had 5 transformations, I'm not imagining what it would be, but suppose you made 5 different movements or a change in coordinates. So you've got 5 of these objects. Internally takes the product of these. So if you have 5 in the global and 12 in the local, you're going to get 60 copies. Very powerful. You can do lots of replications in a very easy way. There is another method for replication that works in conjunction with these two methods, and it's known as levels. It's something that would be more appropriate in an advanced course to talk about using levels as well. Just be aware that there are levels. Well, you can see the statement down here. And the difference between levels and global and local is with levels, you can do multiple parts. You have a marker at the beginning and a marker at the end, and everything in between those markers get replicated by the levels. So you can have hundreds of parts all being replicated with the level command.